In this video, I'm going to be talking about some of the properties and laws of logarithms. If you don't know what a logarithm is, or you need a reminder, then watch my video on that. Before we begin, let's just quickly recap the definition of a logarithm. So if we have an equation that says b to the power x equals n. So in this equation, b is called a base. X is the exponent, index or power, you might know it as, and n is just a number. So we've got a base with a power and the answer gives us a number. Logarithms are used to rearrange this equation, so it is just a way of rewriting this equation, and the way we write it is log to the base b of n equals x. So this is telling us the power that goes with the base b to get the answer n, and that gives you the power x. So again, b is the base, n is just a number, and x is our exponent or power. So essentially a log is just a power. It is a way of rearranging an equation with a power and it's get the power as a subject, but a log is a power. So for example, if we were to write log base 2 of 8, the answer to this would be the power that goes with 2 to get the answer 8. So in this case, the answer would be 3, or the power would be 3. So you can see that all a log is doing is giving us the power. A log essentially is a power. So we could rewrite this equation as 2 to the power of 3, which is log base 2 of 8, equals 8. Because remember, log base 2 of 8, this bit here, is the power that goes with 2 to get 8. So that is the power that we need to put with 2 to get the answer 8. This gives us our first rule, or our first property of logarithms. If we generalise it, we've got a base, and the log base b of a number will equal that number. Because remember again, the log base b of n means the power you put with b to get n. So if we put that with b as a power, we will get n. So our first property is if you have a base raised to a log of the same base, the base and the log essentially just cancel out and you are left with just the n. So a quick example, 3 to log base 3 of 27 would just be 27. The 3 and the log 3 cancel each other out. That is our first property of logs, and it can be very, very useful for rearranging equation and using logarithms to solve difficult equations. So we've got our first property, and our second property is very similar. If we have it the other way round and we have a log base b to get b to the power x, then this means what power do we put with b to get b to the power x? So if I write that out, it means what power goes with the base b to get b to the power x. Well, our answer then must be x. X is the power that needs to go with the base b to get b to the power x. So again, if you have the log b of a number which has the base b and a power, you are left with just the power. The log base b and the b cancel each other out and you are left with just the x. So for example, if I want to know log 2, so the power that goes with 2 to get 2 to the power 4, well, that is going to be with 4. 4 is my power that goes with 2 to get 2 to the power 4. So that is our second property, which can be very useful to remember. So we've got two useful properties, and we're going to quickly look at two more. The first of these two is if I have log b of 1. This means what power goes with b to get 1. The answer to that is 0. If you remember your indices laws, b to the power of 0, or anything to the power of 0, it doesn't matter what your base is, anything to the power of 0 is 1. So if you need to know what power goes with b to get 1, doesn't matter what your base is, the answer will always be 0. There are two exceptions to this rule, which is when you have the base of 1 or the base of 0. Let's have a quick think about what happens in these circumstances. This top one is asking us what power goes with 1 to get the answer 1. In that case, it could be anything. 1 to the power of anything is equal to 1. So in this case, although the answer 0 works, it won't necessarily be the right answer because 1 to the power of anything is 1. The other exception when the base is 0, 0 to the power of anything is 0. So log 0 of 1 doesn't actually work. There is no possible answer. There is no power that you can put with 0. If you try 0 to the power 0, if you try typing that into your calculator, that is actually undefined. It will tell you it is a maths or syntax error purely because of this fact, because 0 to the power of anything is 0, but anything to the power of 0 is 1. So you can't have two different answers for the same calculation. So it is actually undefined. 0 to the power of 0 doesn't work. You cannot do it. So in this case, if your base is 0, that doesn't work. You can't have log base 0. If your base is 1, then although 0 could be a correct answer, it could also be anything else. If you don't know your indices laws, then have a look at my video on that. The third property then, the third useful property, is that log base b of 1 equals 0. Our fourth useful property is if we have log base b of b. So this means what power goes with b, so b to the power what is b. The only way we can get b out is if our power is 1. Any other power will change it. So log b of b is just 1. So log b of 1 is 0 and log b of b is 1. Again, they are useful properties to remember when you are dealing with equations that have logarithms in them. So test yourself to check you really understand these four properties. The properties are written in green on the left hand side, and see if you can use them to simplify down these 5 expressions. The first one then, the base 3 and log base 3 cancel out and leaves us with 4. So the second one, log, remember if there is no base written, it's an invisible 10. A log on its own means log base 10. So here the log base 10 and the 10 cancel out and leaves us with 16.3, because this is asking us what power goes with 10 to get 10 to the power 16.3, so that is 16.3. Again in number 3, the base is 10. So the 10 and the log 10 cancel out and leave us with 2.9. Log 2 of 2, what power goes with 2 to get 2? That is just going to be 1. And log 8 of 1, what power goes with 8 to get 1? That has to be 0. Anything to the power 0 is 1. So hopefully you got all of those correct. Now let's move on and have a look at some of the laws of logarithms. So we've now found 4 properties of logarithms which can be deduced from the definition of a logarithm and a good understanding of logarithm. Now we're going to look at the laws of logarithms. Because logarithms is the inverse of an exponent or a power, the laws of logarithms are very closely linked to the laws of indices. So to really understand the laws of logarithms, it helps if you have a good understanding of the laws of indices. So if you need to, have a look at my video on that. The laws of logarithms then, just like the laws of indices, allow you to combine terms with the same base. So they can be very useful for simplifying equations, and you need to know how to do it. Now you don't necessarily need to understand the proof or be able to prove the laws of logarithms for school maths, but I find that a good understanding of the proof allows you to use them more fluently and more correctly, and it really helps you understand how to use them if you understand where they come from. So we're going to quickly look at where the laws come from, and then we'll look at how we can use them. If you don't want to know where the laws come from, then look in the description below and you can skip to the section where we actually talk about how to use them. Our first law of logarithms comes from the multiplication law of indices, which tells us that if you have two numbers multiplied together with the same base, you add the powers to get your combined power. So what we do is we first of all just let our first term equal x and our second term equal y. So we are just calling our a to the power of m x, so we're saying x equals a to the power of m, and we are calling a to the power of n y. So we're not changing anything, we're just putting some definitions in there. From our definition of logarithms then, we know that log base a of x is equal to m, and log base a of y is equal to n. So this is just our definition of a logarithm. What power goes with a to get x, that will be m, and what power goes with a to get y, that will be n. So back from our original equation from our laws of indices, we can rewrite that as x times y is equal to a to the power of m plus n. X times y, remember in algebra we don't normally bother with the times sign, so we can just write that as xy. X times y is xy. Again, using our law of logarithms, we can say log base a of xy is equal to m plus n. What power goes with a to get x times y? Well, from our definition up here, that is m plus n. But remember, m is log a of x, so we can change our m in this equation to log a of x, and n is just log a of y, so we can change our n into log a of y. So if we rewrite out this equation with log a of x and log a of y instead of m and n, we get log a of xy equals log a of x plus log a of y. And this is actually our first laws of indices, the addition law. So if you've got two logs of the same base added together, you can actually simplify that down to a log of the same base with the two numbers multiplied. Now let's go back to our indices laws and think about what this actually means. Remember, a log is just a power. So if we've got two numbers x and y, and we want the power that goes with our base a to get those two numbers multiplied together, well, what do you do with the powers? You add them. So log a of x is the first power, log a of y is the second power, and you add them together. So that is actually exactly the same as our original index law up here. It is saying the power of the two numbers multiplied together is the same as the individual powers added together, m plus n. So let's just put some numbers in to really show how it works. So if we had log 2 of 8 plus log 2 of 4, we know that we should be able to simplify this down to a log of 2, a log of the same base, by multiplying the two numbers, so multiplying 8 times 4. So let's just check how that works. Log 2 of 8 is the power that goes with 2 to get 8. So that is actually the power 3. 2 cubed is 8. 2 times 2 is 4 times 2 is 8. Log 2 of 4 then, the power that goes with 2 to get 4, that is 2. 2 squared is 4. So 3 plus 2 is equal to 5, we know that. So does that work with what we understand from our log laws? Remember, we said that we should be able to simplify this down by doing 8 times 4, which is 32. 2 to the power 5. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So this does directly correspond to what we understand about powers. So hopefully you see that this law does work, and remember, it only applies of logs with the same base, just as the indices laws apply to numbers with the same base. So if you have two logs added together with the same base, that is the same as the log of the same base with the two numbers multiplied. So let's have a look at our next law. Our second law of logarithms comes from our second law of indices, which is the division law. So when you are dividing numbers of the same base, you subtract the powers. So again, we are going to call our first number a to the power m, we're going to call that x, and we are going to call our second one a to the power n, y. Rearrangement of these gives us log a of x equals m, and log a of y equals n, just as we had for the previous law. Now this time we've got our first number a to the power m, which is x, divided by a to the power n, which is y. So I'm just going to write my division as a fraction here, and that is equal to a to the power m minus n. Using our log laws to rearrange this then, log base a of x over y is equal to m minus n, and as we did before, m is actually equal to log a of x, and n is actually equal to log a of y. So our second log law is a direct comparison to our second indices law, and it states that if you have two logarithms of the same base subtracted, you can simplify that down into a single logarithm of the same base by dividing the numbers. And again, that fits our laws of indices, because remember, the log is the power, so if we want the power of two numbers divided, we need to subtract the individual powers. So again, let's put some numbers in to just double check this works. So if we are asked to simplify down log 3 of 81 minus log 3 of 3, we've got two logs of the same base subtracted, so we can simplify that into a single log of the same base by dividing the numbers. So 81 divided by 3 is 27. Now let's check that actually works by working out the powers. So the power that goes with 3 to get 81 is 4. 3 times 3 is 9, times 3 is 27, times 3 is 81. Take away the power that goes with 3 to get 3, that is 1. And then what power goes with 3 to get 27? That is 3. 3 times 3 is 9, times 3 is 27. 4 take away 1 is 3, so our law is working with those numbers. You can try plugging in any other numbers, but you will find that this does always work. Our final law of logarithms then comes from our third law of indices, which says that if you have a power raised to another power, you multiply the powers. So again, we are going to let a to the power m equals x. We are going to call it x. This time we don't need a y. A rearrangement of this using log laws tells us that log base a of x is equal to m. So if we plug x into our indice law, so we get x to the power n equals a to the power m times n. Rearrange this using our definition of logarithms. So log base a to get x to the power n is equal to our power m times n. Now remember that m is log a of x. So we've got log a of x times by n. Now remember that means n times the whole of log a of x, which is easier to write as n log a of x. So if we compare that to the left hand side of our equation, log a of x to the power n, that is the same thing as n log a of x. So the only difference between these two sides of the equation is where the n is. So if you have the log of x to a power, that's the same thing as the power times log of x. So that is really, really useful, because if you have an equation with an unknown power in it, you can use logarithms to bring the power out, so we can reduce an equation with a power in it into an equation with a multiplication in it. And a multiplication is much easier to find than an unknown power. So if you think about all of our log laws, they all reduce the level of the equation. So the first log law here reduces a multiplication to an addition. If we started with a multiplication, we could use logarithms to reduce that to an addition if we are using our law the other way. We can reduce a division to a subtraction, and now we also have a law that reduces a power to a multiplication. So logarithms are extremely useful for solving difficult equations, particularly equations that involve powers. So let's have a quick look at some examples of how we can use these laws. So if we have log 3 plus log 7, remember they both mean log base 10 if there is no base written there. So we can combine that into a log of the same base by multiplying the two numbers. We are using our first law that we derived down here. 3 times 7 is 21, so that is the same as log 21. If you've got a calculator, check it and you'll find that it's right. Log 2 of 32 minus log 2 of 4, again they are the same base, so we can use our log laws to combine that to a log of the same base by dividing this time because it's a subtraction. 32 divided by 4 is 8. 2 log 4, remember if we've got a number in front, that is the same as if we had log of 4 squared. We can move the 2 up to a power using our last law down here. 4 squared is 4 times 4, which is 16. So 2 log 4 is the same as log 16. And just to double check, 2 log 4 is the same as log 4 plus log 4, 2 lots of log 4. And using our multiplication law, you can combine that into a single power by multiplying the numbers, and 4 times 4 is 16. So it gives us the same answer. 3 log 2 plus 2 log 3, we can't just combine those as they are because of these numbers in front, so we need to move those numbers in front up to the power. So 3 log 2 is the same as log 2 cubed, and 2 log 3 is the same as log 3 squared. So log 2 cubed is 8, so that's the same as log 8. 3 squared is 9, so log 3 squared is the same as log 9. Now we can combine them using our log law because we don't have any numbers in front. So because it's an addition, we need to multiply the two numbers, and 8 times 9 is 72. So 3 log 2 plus 2 log 3 is the same as log of 72. Again, check it on your calculator and you will find that it does work. So pause the video and have a quick go at these questions to check that you understand. So we've got two log base 10s added together, because remember when there's no base written it's log base 10, so we can combine that into a single log base 10 by multiplying the numbers, and 4 times 6 is 24. So log 4 plus log 6 is the same as log 24. Log base 3 of 20 minus log base 3 of 4, we can simplify that down into a single log base 3 by dividing the numbers, so 20 divided by 4 is 5. So 4 log 2, remember we can move the 4 up and that becomes log 2 to the power 4. 2 to the power of 4 is 16, so that becomes log 16. 2 log 4 minus 3 log 2, remember we can't simplify that down into a single log until we get rid of the numbers in front. So we can move those numbers up. So 2 log 4 becomes log 4 squared, and 3 log 2 becomes log 2 cubed. Log 4 squared is the same as log 16, and log 2 cubed is the same as log 8. And then remember, to simplify a subtraction in logarithms, we divide the numbers, so 16 divided by 8 is 2. 2 log 4 minus 3 log 2 is log 2. Now I just want to point out a common mistake that is often made when using our final log law, and that is that if we have something log of 3x squared, a lot of people will simplify that down to 2 log of 3x. Now this is not correct, and let's have a look at why. Log of 3x squared is not the same as log of 3x squared. The 3 is not with the power, the 3 is not part of the base in the 3x squared. What log 3x squared actually means is log of 3 times x squared. So just as when transposing normal algebra, we have to transpose this in the correct order. For example, if we had 3x squared equals 42, you could not square root first. You don't say that that is the same as 3x is the square root of 42. That is not the order that you do it in. You deal with the 3 first, so you would divide by 3 first, and then you would do the square root. So it's exactly the same principles as that. We need to do it all in the correct order, so we need to deal with the 3 first. If we have two numbers multiplied together, we can actually split up that logarithm using our addition log law, which says that we can split it up into log 3 plus log x squared. So we are using our addition laws of logarithm in the opposite way to what we were using them a minute ago. And now we have split the x squared away from the 3, we can now use our log law, our final log law, to write log x squared as 2 log x. Now this is going in the other way to what we've been doing. We are splitting up the equation, but this can be really useful for finding unknowns that are within something like 3x squared, or for reducing exponentials to multiplications for the sake of plotting graphs and finding unknown constants. So just make sure you are being careful. Log of 3x squared is not the same as 2 log 3x. Now we're just going to look at one final thing, which is called changing the base. Now I'll explain what that means. If you have a fairly new scientific calculator, you will probably have a button that looks like this that allows you to type in any base that you like. However, a lot of calculators don't have that button. They only have a log button or a ln button, where log means log base 10 and ln is the natural logarithm, which is log base e. If you don't know what this is, that is explained in another video. But although you may have a calculator that allows you to type in any base, allows you to do this, that you still may be asked to change the base, and it is still sometimes useful to change the base when reducing exponential equations down to linear equations. So it is worth knowing how to do this. Now what I mean by changing the base, for example, is if I have 3 to the power x equals 7, We could, of course, rearrange that to log base 3 of 7 equals x, and if you have a calculator with this button on it, you can type in log base 3 of 7 and it will give you your answer. However, if we do not have that button, we need to change the base either to log base 10 or log base e to allow us to do it. So the way we do that, we know we have an equation with an unknown power in it. Now remember, we have said that we have a log law that reduces a power down to a multiplication, and a multiplication is something that we can solve. So if we use a logarithm of a base that we can do, say log base 10, then we can reduce this down to a multiplication and solve it. So the way we do that is we take logs of both sides, and I'm using log base 10 because I have a calculator that will do log base 10. We could use ln or log base e. It doesn't matter as long as you do the same to both sides, because if 3 to the power x equals 7, that means that they are the exact same thing. So log of 3 to the power x must be the same as log of 7, because 3 to the power x is 7. So now we've got a log in front of both sides, we can reduce this power here to a multiplication using our final log law that we derived, and we get x log of 3 equals log of 7. So now this means x times log 3, so to get the x on its own we simply need to divide by log 3, so we get log 7 divided by log 3. So if we compare this to our original rearrangement of the equation, x equals log 3 of 7, we know that that is also equal to log of 7 divided by log of 3. So that actually works with any base, and the general rule is if we have log base a of b, that is the same as log of b over log of a. And we could have used any log we liked in the beginning. Like I said, we could have had our natural logarithm log base e in there. As long as both of them are the same, you can change the base to any base you like, but we often use log base 10 or log base e, which is ln, because that is what most calculators can do, although these days a lot of calculators can allow you to type in any base you like. So that is called changing the base, and it is another useful property of logarithms. So I keep mentioning that logarithms are very useful for when you have an unknown power, because a logarithm is a power. It allows you to rearrange an equation to get the power as the subject. So there are actually two different ways to go about solving this equation here. We could straight away use our definition of logarithm and say that log base 5 of 3 must be x plus 2, and then to get the x on its own we simply subtract the 2. So if you've got a calculator that allows you to type in any base, you can type in log base 5 of 3 minus 2, and that will give you x, and if you type that in you should get minus 1.317. You can then check this in your original equation, type in 5 to the power of minus 1.317 plus 2, and that will give you 3. However, you often need to do this without using that button, without using log base 5. So we can do it in the same way that we derived our changing the base law a minute ago, which is simply to write log in front of both sides, because if 5 to the power of x plus 2 is 3, then log of 5 to the power x plus 2 is the same as log of 3. Now we have logarithms, we can bring the x plus 2 out the front using our log laws, and that becomes x plus 2 lots of log 5, and that is equal to log 3. Now I've put the x plus 2 in brackets here. That is vitally important because it is the whole power times log 5. We then can get the brackets on their own, the x plus 2 on its own, by dividing by the log 5. So x plus 2 is log 3 divided by log 5, which means that x is log 3 divided by log 5 minus 2. And again, if you type that into your calculator, you get minus 1.317. Now this method is a little bit longer, but in some cases you will be asked to do it using that method, and in other cases you will actually need to use this method. If you have a whole equation, you might need to use this method to linearise it, so it is well worth knowing. So check your understanding of logarithms, pause the video and have a go at these 4 questions. So for this first one, you could use the definition of logarithms, but for the sake of the people that don't have a calculator that does that, I'm going to do it the long way. So I'm going to put log in front of both sides. So log of 3 to the power x plus 1 is the same as log of 80. And then I bring my x plus 1 out the front. X plus 1 log 3 equals log 80. So x plus 1 is equal to log 80 divided by log 3. Now I've done a slash there, that is just divided by, I ran out of room. And then x is going to be log 80 over log 3 divided by log 3 minus 1 to get rid of this plus 1 and get x on its own. If you type that into your calculator, you will get a value of 2.99. And then remember, check your answer. 3 to the power of 2.99 plus 1, so 3 to the power of 3.99 will equal 80, which makes sense because 3 to the power of 4 is 81, so it's just a little bit less than 4. So for question 2, I'm going to actually get rid of the squared first to simplify the equation. So log 3 of x squared, remember, is the same as 2 log 3 of x, and that equals 4. So I can then divide both sides by 2, and I get log 3 of x equals 4 divided by 2, which is 2. Now this just simplifies down my equation so I don't have a power, so that now when I rearrange it using my definition of logarithms, this means that the power that goes with 3 is 2, and that will give us x. So 3 squared is x, so x must be 9. Question 3 then, I'm going to use my logarithm subtraction law to simplify this down into a single logarithm by dividing the numbers. So I've got log of x divided by 3 equals 4. And then I can use my definition of logarithms to rearrange, remembering that log on its own means base 10. So I've got 10 to the power 4 equals x over 3. X then is 3 lots of 10 to the power of 4, which you could leave it in that form, or that is the same as 30,000. Finally, question 4, I'm going to first of all divide by 12. So I get 1 plus 4 to the power x is 18 over 12, which simplifies down to 3 over 2. Remember, we need to get the base and the power on its own to use our definition of logarithms to release the x. So I need to get the 4 to the power of x on its own first, so I'm going to take 1 away from both sides. 3 over 2, take away 1, which is 2 over 2, it leaves me with 1 over 2. So 4 to the power x equals a half. I can now use my definition of logarithms to rearrange because I have a base and a power on its own. So that gives me log base 4, and I want to get a half, is equal to x. So if you type into your calculator log 4 half, that will tell you that x is equal to minus a half, or minus 0.5. If you don't have a button that allows you to do that, remember you could have just taken log of both sides, and you would have got log 4 to the power x equals log half. That rearranges to x log 4 equals log half, so x is equal to log half over log 4, and you can type that into your calculator to get the answer minus a half, or minus 0.5. Alternatively, you might have actually known what x was at this stage here without even having to use logarithms. If you know your indices laws very, very well, you might have known that the answer to that the power required would have been minus a half. So I hope that you now understand the properties and laws of logarithms and how they can be used. There will be more videos on the uses of these, such as reducing equations to linear equations, reducing exponential equations to linear equations. And remember, if you are struggling with the definition of a logarithm or the general use of logarithms, then do have a look at my video on that. Logarithms are often found to be a lot more difficult than necessary. They are not as hard as they first appear. As long as you get confident and happy with the definitions and rules, they can actually make life a lot easier in certain circumstances. So good job, and I will see you again soon.